Okay, we start in chapter 2, and we're going to be developing the idea of a derivative when we have a function of several variables. So here they say that we have a familiar formula, volume as a function of the radius, and here is the surface as a function of the radius. These are functions. There are less geometric types of functions. There are many types of examples. But the idea of a function is that in any case we have a domain set, and we have a codomain set, and then we have a rule of assignment. So this is a basic idea of functions. So this is a picture of that idea. So we have a domain set. So in this previous case, like here, the domain set would be the set of all possible R values that are allowable. So that would mean, for example, that we wouldn't have a negative R, right? We wouldn't talk about negative radius, although actually we did talk about it in the previous chapter. But generally, when we're talking about the volume of a sphere, we wouldn't. So the set of allowable values would not include negative numbers. Maybe all real numbers that are non-negative, or maybe all positive real numbers might be the set of inputs. So that's what this set stands for, and we call it the domain, and they're denoting it by X. And then we have what they call the codomain, and that's another set, and that's the set of values that the function maps to. So here, for example, I guess since R could be any positive number, then really probably V could also be any positive number. Okay, so that we would say that the codomain is also the set of all non-positive numbers in that particular case. And then we have a rule that assigns values. So like, for example, if R equals 2, then this would be 2 cubed, which would be 8 times pi and 4/3 of that. So whatever that equals, 4/3 pi of 8, that would be the, the map would go from R equals 2 to whatever that number was, 4/3 pi of 8 times 8. So that would be the rule. So the rule takes elements from the input and maps them to elements in the output, or elements from the domain and maps them to elements in the codomain. So instead of that, the example of the volume, here's another example. So they say, for example, U.S. citizens and social security number. So we could talk about a function which takes each citizen and assigns it a social security number. So these would be people, and then these would be their social security numbers. Social security numbers is like kind of an ID number. And to be a function, you can only have if one element here going to a single element here. So that's part of the definition of function. And then we also talk about the range, and that's the little bit, maybe we might think of it as a smaller set than the codomain. The codomain is the set of kind of all possible values for the output of the function, but the range is the actual values that actually get hit by the inputs. So here, maybe the whole codomain is like this entire bigger set, but the range is just this and this both go to here, and this both go to here. So if we only had these 3 points in the domain, then the range would just be these 2 points, as opposed to the entire possible set. So they say the range of a function is the set of those elements of y that are actual values of f. That is, the range of f consists of those y in y such that f of x equals y for some actual x in x. Using set notation, we'd say the range of f equals the set of all y in y, such that y equals f of x for some actual x in x. Okay, the next definition is a useful definition about functions. A function from x to y is said to be onto, or also they use the word surjective, if every element of y is the image of some element of x. That is, if the range of f equals all of y. So what it means is that if this is the codomain, then every element in the codomain actually gets hit by the mapping of some element here to here. There's nothing that's missing. So for example, this picture, this element b doesn't get hit by anything over here. So this function would not be called onto because it's not, doesn't touch everything. It's not onto this set, that I guess we could say. So anyway, this picture would not represent an onto or surjective function. And then there's another useful definition, that is 1-1, or I call it 1-to-1, or it's also use the word injective, if no two distinct elements of the domain have the same image. So going back to here, we have, or here, for example, we have this element and this element both going here. So that is not 1-to-1. This is still a function, right? Because we don't have one element going to two places over here, but we do have two going to one, which is allowed as a function, but it's not a 1-to-1 function. So because we have this situation, this is not 1-to-1. Also here, this is not 1-to-1 because of what's these two are going to the same thing. It is, it's also not onto, right? This one is also not onto, whereas this one is onto. Okay, let's think about a common example, which is f of x equals x squared. And this is a function. The inputs are r, and the codomain is also r. But what about the range? So the domain and codomain are r, but the range of f is not all of r. The only elements that actually get hit by this, if we put in x, we only get out non-negative numbers. So from 0 to infinity would be the range. So the codomain is all of r, because it says codomain is r here, but the range is the only set of values that are actually hit. So that's all non-negative numbers, or this is a notation for that. They also say that this is not onto, and that's because not all of the elements in R get hit. Since the codomain is strictly larger, this is strictly larger than this. Note also that this function is not 1-to-1 because we can have both 2 and -2 get mapped to the same element. Remember that this was not 1-to-1 because we had two elements going to 1, and this function x squared is also an example of that because both 2, if this is 2 and this is -2, and this function is x squared, they both go to 4. So that is not 1-to-1. They say 1-1, but I'm going to say 1-to-1. So let's just read how that's written again. Note that f is not 1-to-1, since f of 2 equals f of -2. That is, they're both equal to 4. But 2 and -2 are not the same. Okay, here's another example. You can think about this one and read it. Okay, now we're ready to think about functions that of more than one real variable. In most general terms, these are functions whose domains are subsets x of Rn. So we're talking about functions whose domain is Rn or some subset of Rn, and whose codomains are Rm. So also not just r. So here we just have a function from r to r, but we're going to be talking about functions from, let's see, in general, functions from Rn, so instead of r, Rn, and to, not r, but Rm, for some positive integers n and m. Now it doesn't have to be all of Rn, it could be a subset of Rn. So we say that a function is a mapping from a subset of Rn to Rm. Actually, we probably could say to some subset of Rm, but they say something like, for simplicity, we'll take the codomain to be all of Rm. Okay, so let's look at some examples to make this a little bit clearer. So first, we're going to take a function from R3 to R. Now, we said that we can have more than R here, so we can have R2, R3, R4, and so on. We can also have more than R here, but here we're only having R3 to just R. Okay, but anyway, this is a first example. So the function is called t, and it's a function from R3, so that means we have to specify 3 inputs. So we have x, y, and z, and this is the output. So this output has to be in R, and this is in R. These are, if we do x, y, and z are scalars, and we multiply 2 of them, multiply another 2 of them, multiply another 2 of them, and add that up. That's a scalar. So this is a function from R3, because this is R3. This is an element of R3, but the output is just R. We can think of t as a sort of temperature function. So you give it a point in space, that means you have to tell it the x, y, and z coordinates of the point in space, and then it's going to tell you what the temperature is at that point. So this is a function from R3, the set of points in space, to a number, so that number might be the temperature at that particular point. So given a point x, so x being in R3, then t of x, because we said it's t of x, y, z, but that's, so we can write that briefly as t of x, as succinctly as t of x calculates the temperature at that point. Okay, next example. So now we're going to take a function from Rn. Before we did our last example was R3, but we're talking about Rn to R. So the input is going to be an element in Rn. So instead of just x, y, and z, we can have like x1, x2, x3, all the way up to xn as an input. And the output is just going to be a number. And here's the function. But what is this? What does this mean? Well, this is not new to us. This means what? The norm of this point in Rn. And we know what that means. And it means the length or the magnitude of the vector. And we know how to calculate that. For example, one way to calculate it is to do x dot x and the square root, right? The dot product of x with itself and then the square root. But anyway, it's the length or the magnitude of x, which is a number. So we're putting in a vector, something in Rn, and getting out a number. This is a length function in that it computes the length of any vector x in Rn. Note that L is not 1, 1, or not 1 to 1. Why is that? What does 1 to 1 mean again? It means this is not 1 to 1 because we have 2 values here going to 1 value there. That's not 1 to 1. But why is this not 1 to 1? Why is this not 1 to 1? Well, they just give a quick example. remember EI and EJ means the unit vectors in, this is the unit vector in the ith direction, and this is the unit vector in the jth direction, right? We have many directions here, so to speak, because it's Rn. If we only had R3, this might be I, and this might be J, but anyway, or this might be K. Anyway, we just mean one of the unit vectors and another of the unit vectors, but their lengths are always, the unit vectors' lengths are always 1. So we have that this and this both go to 1, but the inside EI and EJ are not the same. So that's not 1 to 1. We have two things going to the value 1. That's not allowed in terms of 1 to 1. And they also point out that L also fails to be onto, because if we say the codomain is all of R, but we can't get negative numbers for the length. So since the length of a vector is always non-negative. Okay, let's do another example. Consider this function. So we put in x, and I guess this is where x is a vector in R3. We put in x, and what we do is we take x and divide it by its norm, or its magnitude. So we saw this a little bit before, and hopefully you remember that this vector will be in the same direction as x, but will have unit length, or length 1. And you can see part of that because, we showed this before, but you can see part of that because this is x divided by a scalar. So x divided by the scalar, or x multiplied by a scalar, is always in the direction of x. So it's going to be in the same direction as x, and then we showed that this is going to have length 1. So this is a unit vector in the same direction as x. Now up here, we had a function t from R3 to R, right? We had an input, which is the same kind of input as this is. This is also in R3, and we had this example was also from R3. This function went from R3 to R, but where does this function go to? We put in a vector. Do we get out a scalar like we did up here? No, we get a vector out. So this is what? A vector function, this n, is a function from R3 to R3, not R3 to R. Now they're going to say a little bit, make a slight note about that, but basically let's say that right now. So this is a function from R3 to R3. Now they say, note that n is not defined if x equals 0, because then the denominator is 0. So the largest possible domain for n is R3 minus 0. So we really can't include 0 as part of the domain, the 0 vector, that is. The range of n consists of all unit vectors in R3. Okay, so the range is all unit vectors in R3. Oh, sorry. It's not all of R3. It's only the range is all unit vectors in R3. The codomain, I guess, could be all of R3. The function n is called the normalization function. That is the function that takes a non-zero vector here in R3, and returns the unit vector that points in the same direction. So that's called the normalization function. Okay, example 7 points out that a function can be given instead by some kind of formula like we had here, or here, or here, or x squared. Sometimes we give we explain what the function is by means of a table. So here is a function where we put in the temperature and the wind speed. So of course you know that when it's very cold, these are temperatures in Fahrenheit, but it doesn't matter. When it's very cold, this is very cold, and the wind speed is high, then it feels even colder. So even though the temperature is 15, when the wind speed is 20, it feels like it's -2. So so this is a function of from R2 to R. Why from R2? Because we put in two values. We put in the temperature and the wind speed. So that's two different variables. So, and each of those are numbers. So we could call it from R2, and then the output is just a single number. So it's a function from R2 to R. Okay, now here's a function from R to R3. What does that mean? So the function is f of t. So I think we've seen something like this where we had what we called a vector valued function. I think we saw that. Anyway, let's see what happens here. So the input is just t, and the output is what? It's this triple. You have, how many commas do we see here? 1, 2. So that means the output is 3 separate elements, which means it's in R3. So this is a function that takes as an input just t, but gives us back basically a vector, because there are 2 commas here. So it's from R to R3. Okay, the range of f is the curve in R3 with parametric equations. X equals the cosine of t here, y equals the sine of t, and z equals t. If we think of time as a parameter, then this function traces out a corkscrew curve called a helix, shown in figure 2.6. So basically, you know that cosine t sine t gives you a circle. So you just be spinning around in a circle as t increases. So when t starts out at 0, the cosine is 1, and the sine is 0. And then as t increases, the cosine gets smaller and the sine gets bigger, and so on. But anyway, you're moving in a circle as t increases. But here we have a third variable, so we're talking about not just in the plane, but in 3 space. So the third variable is just t. So that means as t increases, the height of this output increases. So we're going around in a circle, but we're also moving up. So we get this corkscrew or helix. Okay, the next example, we can think of the velocity of a fluid as a vector in R3. So here we have water or some liquid being poured out of a glass or a jar or something, and the velocity of the water is a function from R4 to R3. How come it's from R4? Well, let's take a look. So here's the function that we're going to just going to make up this function, but it is from R4. So why is it from R4? Well, x, y, and z are the position. So like right here. So if it was just without the last component here, without that t, it would tell us what? Once we put in the position, then we would be getting out a vector. Let's ignore that we had a t here. So then we would be getting out a vector, right? Because you put in these, and then you plug them in here, and you get out a vector. So what does that mean? So the vector so like right here, I put in this position, x, y, z. This point has a position, so it has x, y, and z coordinates. I put that in, and I get out some vector. What is that vector? The vector is the direction that the fluid is moving. So it might be moving in this direction, it could be moving in some other direction. And the length of the vector is supposed to indicate the velocity, the speed, so how fast it's moving, but we also have the direction that it's moving. So we need a vector to express that. So it's got a direction and a magnitude. The magnitude means how fast it's moving, and the angle or the orientation tells you in what direction it's moving. But actually, this is a function from R4, so we don't just have x, y, and z here. We have t. What does that mean? That means that we're going to allow, we just said, okay, at this point it's moving in this direction, but that's at a particular time. Maybe at another time it's moving faster, so we'd have a different vector, or it's moving in a different direction. So the water at this location could be moving faster later on, or it might be moving in a different direction later on. So anyway, it depends on time as well as the position. So we have as the set of inputs x, y, z, and t, and then this, whatever x, y, and z and t are, we put that in here, we do all this stuff, we get out a vector, still a vector in R3, still a vector in R3, telling us in what direction the water is moving and how fast it's moving. The magnitude will tell you how fast it's moving. So let's read that. We can think of the velocity of a fluid as a vector in R3. So it's in the output is R3. This vector depends on at least the point at which one measures the velocity and also the time at which one makes the measurement. In other words, velocity may be considered to be a function v from R4. Now, well, let me just finish that. From R4 to R3. Now, this x, remember, just means that we don't have to take all of R4. It might be some subset of R4. So that's what this is doing. A little bit confusing, but we have to get used to that. So you can just, for almost all the time, we can just say it's from R4 to R3. So anyway, velocity may be considered a function v from R4 to R3. The domain x is a subset of R4 because 3 variables, x, y, and z, are required to describe a point in the fluid, and a fourth variable is, okay, anyway. Figure 2.7, for instance. Okay, so for instance, such a function might be given by this. Of course, we could change this in any way. Like we could make this a cube, and that would mean that it was moving in a different way. But anyway, you may have noted that the expression for v in example 9 is considerably more complicated than those for the functions given in 4 through 8. This is because all the variables and vector components have been written out explicitly. In general, if we have a function from Rn to Rm, then for x in the domain can be written like this if we want to, and f, the output, can be written in terms of its component functions. Okay, I'm going to stop here and then come back to this.